Okay, in this video I'm going to run through how to fit a curve to experimental data. So this is going to be a general technique for when you know the functional form of the data or the expected functional form of the data, and the relationship between data on the x-axis and the y-axis is nonlinear. There are plenty of videos out there on how to carry out so-called linear regression, which is a lot more straightforward than this, but this is for when you have data which has a slightly more complicated form. Okay. So here's some example experimental data. So on the y-axis we have some values, which in this particular case is reflectance, and on the x-axis we have our independent variable, which in our case is frequency. So we have some sort of system where basically the energy is absorbed at a particular frequency, around 9.24 Hertz, and at other frequencies the data is not absorbed so well. And what we'd like to do, we'd like to basically fit that data to some function which we know. In our case we're going to use a Lorentzian function, but the technique we're following is very general, can be applied to basically any functional form, as long as the function is differentiable with respect to the parameters of interest. And you can do this for a variety of reasons. Basically, excuse me, you could have some experimental data and you want to extract some parameters from it. That's one of the main reasons. Okay, so in our case, we're going to use the Lorentzian function because that's what we believe our data is representative of. So we have the function here on the left-hand side, and we have four parameters actually. We have our input frequency, which is f, and then we have four other parameters which characterize the response. So the first one is Rmax, which stands for maximum reflectivity, and that we can sort of describe as being the maximum value of the background of our function there, which in our case is approximately 0.9. We have another function R0 here, which is basically the minimum of our Lorentzian function here. We have F0, which is the frequency at which this minimum takes place. And we have a parameter delta W, which sort of characterizes the width of this line shape. Technically, delta W is the width of the function at half of the maximum peak. So basically Rmax minus R0 divided by 2, and it's the difference between the two frequencies at that reflectivity. So we actually have four parameters which we're going to fit here, which is quite a lot normally, but I'm just using this as an example to show how you would go about fitting a function. Okay, so let's look at the procedure we're going to use. We're going to use a technique called Gauss-Newton, and it proceeds as follows. Firstly, we have to differentiate our function, our model function, with respect to the four parameters which we're using. In your case, it may not be four parameters. It depends on the function you're using. So we have these four parameters: Rmax, R0, F0, and delta W, and we have to basically differentiate, find the analytical solution to the derivative of our model function, which is the Lorentzian function, with respect to each of these parameters. The next step is to come up with some initial guess parameters for each of the parameters which we're going to be fitting. So we indicate these are guesses, these are our first guesses, with the superscript 0 here. And how we'll do that we'll come to in the video. The next step then is very simple. We just take each of these guess parameters and put them into a column vector, which we label beta. So the next step is to evaluate our model function, which in our case is the Lorentzian function, and we evaluate it using our initial guess parameters and our input, which is the frequency. We then evaluate the residuals, which is the difference between our calculated values and our experimental data. And our experimental data here is labeled by Y, and we do this at every position of experimental data, indicated by the subscript I here. Next thing we have to do is evaluate what's called the Jacobian, And this is basically a matrix which consists of a number of rows, which is equal to the number of experimental data points, and a number of columns equal to our parameters. So we have 4 parameters, so we have 4 columns, and in our case we have 11 data points, so we have 11 rows. And basically what we need to do is differentiate our model function with respect to each of the parameters and evaluate that derivative using the experimental data, the experimental input, independent variable, which in our case is frequency, and then fill up the matrix. And then the next step is to carry out some matrix algebra indicated by this function here, which will allow us to update the parameters. So we have our initial column vector beta superscript s, and then by carrying out some algebra using the Jacobian matrix and the residual function, we can then evaluate which a slightly more refined set of variables. Then after we've done this, we evaluate the residuals squared, and calculate what's called the sum of squares, and then we check whether this value is low enough that we accept the solution. And finally, we will be repeating this process until we have convergence. Okay, so the first step is to find the derivatives of our function, our model function, with respect to each of the variables which we're going to parameterize our experimental data with. So this is our function at the top here, and we have to evaluate each of these derivatives. So the Lorentzian function is notated by capital L. We have to find the derivative with respect to each of our 4 variables, Rmax, R0, F0, and delta W. So let's start with Rmax. This is a reasonably straightforward one. We see that basically our Lorentzian function is linear of Rmax. So in that case, all we do is we just drop the power by 1 multiplied by the power, which of course just means we get rid of Rmax. So that's a very straightforward one. It's just basically the same function, but with the Rmax value set to 1. Okay, now we have R0, which is our second parameter. This is our Lorentzian function, and our R0 is inside of the bracket this time, so we have it here. So in which case we can rearrange the function and just create 2 fractions. And here we see we have a term on the left-hand side inside the brackets depends on R0, and a term on the right-hand side is just a constant with respect to R0. So then when we take the derivative, we can ignore the second term, and we just get this value at the bottom. So this is the derivative of the Lorentzian function with respect to R0. Okay, and the third one is with respect to F0. So once again, this is our Lorentzian function, and our F0 is inside of the brackets here, and it's actually a very complicated dependence. So to work out this derivative is not particularly complicated. I mean, as long as the function is differentiable, you can always find a derivative. It's just a case of it being time consuming. So for the sake of this video, I've just written out the answer to this derivative. I've also uploaded a sort of appendix video which shows how you go through and evaluate this derivative in case you're interested, but it is reasonably dull and it just involves applying the chain rule over and over again. So just for the sake of keeping this video short, I'm not going to bother doing that. And the final parameter is delta W. And if we look at our Lorentzian, once again, we find it's inside a bracket, it's squared, and it's at the top and the bottom of the fraction. So it's actually quite complicated to evaluate. Well, not really complicated, but it's just time consuming to evaluate. So I'm not going to do it. I'm just going to give you the answer, which is as follows. Okay, so that's our 4 derivatives. And we have them all here. The derivative of L with respect to Rmax, F0, R0, and delta W. So that's all the terms we need, and we'll come back to using these later on when it comes to refining our parameters. Okay, so the second step is to define the guess parameters. So the way this algorithm works, this is the Gauss-Newton algorithm, like I said, it does require you to come up with some initial parameters. And the reason for that is this is a recursive algorithm, so you need to start somewhere. So it depends exactly on what you're doing, what function you're trying to parameterize, and what your data is like, how you go about doing this. All I've given here is one way in which you could do it for a Lorentzian line shape with the data we have. And you do need a reasonable starting value, otherwise the algorithm will not converge. So I'm just giving you an example of how you do this here. So in our case, we have our max. This is our first parameter. So let's look at the data. So sorry, this isn't the data. This is a calculated value of the Lorentzian. And as we know, this is basically a multiple, something you multiply the Lorentzian by to give you its maximum value. If you just set our max to 1, the blue line at the top, where it's basically flat, will just be equal to 1. So we can use this and then say, okay, in our experimental data, the maximum is about 0.9. So we could approximate it to be 0.9. If you wanted to do this algorithmically, the way to do it would just be to look through all of your data and take the maximum value. And we identify that as being the value when the frequency is 9.3, and we have a value of R max of 0.896. Okay, so we can use this as an approximate value to start with. Okay, R0, this is the next parameter. And as I said before, this is just basically the minimum value of the Lorentzian line shape. And we see here it's just over 0.3 for this evaluated function. So what would we do for experimental data? Well, the obvious thing, I suppose all you can do is just go through, look at the data and take the minimum. So in our case, we have a minimum at 9.24, and the reflectivity, the minimum reflectivity leveled by R0 is approximately 0.4. And if you're going to do it algorithmically, you look through the data and we'd find a minimum value of 0.396. Like I say, you don't need to be particularly accurate, you just need some starting seed values which are sensible, and then you can let the algorithm do the rest. So let's start with that. Next one is F0. So as I said before, this is the frequency at which this minimum value is. So again, we just look at our experimental data, identify the minimum value of this function, and work out what frequency, what the frequency is at which this data is a minimum. So in our case, it's 9.24, and we can identify there in the data. And finally, we have delta W. So this one's slightly more complicated. As I said before, it's the width of the line shape at half of the maximum. So how do we find this experimentally? Look at our data, and basically, I mean, there are a variety of ways you can do this. You could probably look through the data algorithmically and then find the closest values at which the peaks are half. If you're just going to do it by eye, we would identify these 2 points here and say what's the difference between them in frequency. And we'd say, okay, it's 9.25 minus 9.23, which is 0.2 Hertz. Like I say, when it comes to carrying out this algorithm, you don't need to be too accurate. You just need to have some reasonable starting values and then let the algorithm do the rest. Okay, so when we have these parameters, the next thing you do is you put them into a column vector. So we label this vector beta, and because it's the initial starting parameters, we use a superscript 0. And we have to choose an order. Doesn't matter as long as we're consistent throughout our algorithm. We just do it in the order that I identified these parameters: R max, R0, F0, and delta W. And we just fill this vector with these values as we identified in the previous step. Okay, so step 4 is evaluate the Lorentzian. So we now have these starting parameters. We have R max, R0, F0, delta W. With that, we can just enter in the frequency at which we've measured values experimentally, evaluate the Lorentzian, and then just make a note of these values, which is what we've done here on the right-hand side. And if we plot these, you'll see, okay, we have the experimental values in the red dots, and the blue line there is the Lorentzian calculated for a lot more values to give us a continuous line there using our starting parameters. So you can see that the line shape is reasonable, it's a reasonably close fit, but it's not perfect by any stretch of the imagination. So that's what we're going to do. That's what the Gauss-Newton algorithm is going to do. It's going to take this calculated line shape, fit it to our experimental data as best it can, and then we're going to use these parameters for whatever reason we want to. Okay, so we've calculated the Lorentzian. Now we can calculate what's called the residual. So this is just the difference between the calculated values and our experimented values. Basically, it's a sort of error on each point, and it allows us to know how good our match, our function is to the experimental data. So it's characterized by this function Ri. So there's a value for it at each experimental point, and here we calculate it, and it's listed in the table here on the right-hand column. And then we can just put each of these values into a column vector, and because there are 11 data points, there are 11 elements in our column vector, and this is the residual vector for initial starting values. So that's why we have beta 0 inside of the brackets there to indicate that this is the residuals calculated for the set of parameters we've used as our initial guess. Okay, so step 6 is the most complicated one. It's to evaluate the Jacobian matrix. So as I indicated briefly at the start of this video, the Jacobian matrix is a set of derivatives. So we notate it with the subscripts I and j. There are n columns indicated with a subscript j, and there's one for each parameter. So that's why we have a subscript j for each of the betas, because the beta represents our parameters. And we have m rows, and that's indicated by the subscript I. And there's one for each data point. So in our case, we have 4 parameters and 11 data points. So in that case, we have a matrix with 4 parameters, so we have 4 columns, and we have 11 data points, so we have 11 rows. And as I said before, the data points are the rows, so that's indicated with these values I, and the parameters are notated with the subscript j. And as long as we keep the order of our parameters the same, that's all we need to do. The actual order in which you evaluate them is arbitrary, of course, because they're just parameters. You just choose which one you stick where, but you need to be consistent. So if Rmax is at the top of our column vector for our initial parameters, it needs to be in the left-hand column for our Jacobian matrix. Okay, so that's what you do. So how do you fill these elements? So basically, it's just the derivatives we calculated earlier. So we have the derivative of Lorentzian with respect to the parameters. So let's just as an example, look at the top left position, the J11 position. So in this case, we're looking at I equals 1, so that's the first data point in our matrix, and the first parameter, so that's Rmax. So beta 1 is equal to Rmax. This is from our column vector of parameters. And in that case, we can just replace the derivative on the bottom with respect to Rmax. We calculated that before, so this is the result, and that was at the start of the video. So all we do, we just set f equal to the value at the first data point, and then we can evaluate this using all of our initial parameters. And I've just put the superscript zeros here to indicate that we're evaluating this at our initial parameters. And because this is our first data point, we evaluate this function with an input frequency of 9.2. Using our initial parameters, we have everything we need to know to calculate the value of this derivative at this position. Put in these parameters, and this is the value we get. We get 0.9645. And then we can put that into the top left-hand position of our matrix and proceed as usual. So for the first data point, we will just evaluate each of these derivatives with respect to each of the different parameters. And then we go down through our matrix for each of the rows and just replace the frequency with the different data points, the frequency at which we measure these data points. Okay, so we've completely filled our Jacobian matrix now. So we just need to do some algebra. So this looks reasonably complicated, but it's not really. If you have a J with a superscript T, that's just a transpose. So for those who are unfamiliar with that, that's just replacing all the rows and columns. So if we have a 4 by 11 matrix, the transpose will be an 11 by 4 matrix. And the interesting thing, or the only difficult thing, so this is our Jacobian matrix. And you subtract this column vector with 4 elements from our initial guess, and that will give you your updated parameters, which we indicate with a superscript 1. So that's how you go from your initial guess to a refined guess using the Gauss-Newton algorithm. After you've done that, the next thing to do is check for convergence. So the way we do this is we evaluate the sum of squares. So after you've updated your parameters, you look at the residual squared for each of the data points and sum them up. And as I said before, the residuals are just the Lorentzian calculated using our parameters for each data point, subtracted, and then you subtract the relevant data point from that. And here we have it calculated for us. And you see in the right hand column here is the residual squared for each of the data points. And you take the sum of these values and you get a value of 0.059. Okay, so basically when it comes to this, you have to decide how accurate you want it to be. Every time you carry out this algorithm, every time you loop through and update your parameters, you'll get closer to the solution if it's working. And you then have to decide how accurate you want to be. So you have to define the convergence parameter, and then you basically say once your sum of squares gets below this, you're happy with the answer and you accept the result. The sum of squares you choose will depend completely on your function, your experimental data, and the number of data points. If you want to be slightly more sophisticated, you can just say, for example, take the sum of squares and normalize it to the number of data points. But still, you do have to use a little bit of judgment to decide what's an accurate value of the convergence parameter. And then once you've done that, you just repeat. So once you've updated your set of parameters, we now have we've carried out our matrix algebra, and we have an updated set of parameters which are labeled beta 1. We've checked for convergence and decided it's still not quite accurate enough. So we take our beta 1, carry out the same algorithm, work out the Jacobian once again, work out the residuals, carry out this algebra, update the parameters, and now we get beta 2. And then we just continue doing this over and over again until convergence is reached, or we time out. We have to have some sort of break condition in our loop to stop us running into an infinite loop if the data is such that you'd never reach your convergence parameter. And that's basically the algorithm and how it works. So it is reasonably straightforward. The only complicated thing is carrying out this matrix algebra here and inverting the matrix. Like I say, other than that, it's all reasonably straightforward. You just need to make sure you have good guess parameters before you start it. So I'm just going to run through and show you the example here. So we have our experimental data with the red dots and the initial calculated Lorentzian line shape with the blue line. So this is the first step. This is just using our guess. And then after we run through the algorithm, update our parameters, we get a second guess, which is like this. Looks pretty good, much better than before, but it's still not great. Update it again, we see the frequencies moved. And the fourth step here, we have our exact match. And this is the best it will get in our case. So you find that in our case, actually the minimum frequency was missed when we took our experimental data. And that's why doing this sort of thing is very helpful, because you may take some experimental measurements, and you may, if you're doing something like this, miss certain aspects of the data, but you can fit the data and then you can extract the minimum frequency and the minimum reflectivity. And okay, so that's basically how you go about doing this. If you have any questions, just post them below in the comments. And as I said, there's a link in the comments for A, how to invert the matrix, and B, going through the derivative of the Lorentzian with respect to F0, in case anyone's interested in how you do that. Thanks so much for watching.